What did you hear? What did you say? 8x squared plus 18x plus 12. And that's it, yeah. There you go. We can all multiply polynomials. It's just a matter of being careful, right? Because we can multiply, we can add, we can subtract, we can collect like terms. None of these things are tricky, right? But what we're about to do is called factoring, right? And factoring, you could say factoring is unmultiplying. Unmultiplying. Or you could say it's like the opposite of multiplying, right? So generically speaking, if you can take f of x, right, and you can break it into, let me say p of x for a polynomial, and you can break it into, say, f of x times g of x, where these are both polynomials, then this is called factoring. So you can take a given polynomial and break it into a product of two polynomials. If you can do that, that's said to be, that's factoring. So if you look at some of these examples backwards, they're examples of factoring. For example, this c to the fourth minus 256 factors to c plus 4 times c minus 4 times c squared plus 16. This guy factors as that. This 4x squared plus 13x plus 10 factors into 4x plus 5 times x plus 2. This b squared plus 2b plus 99 factors into b plus 11 times b minus 9. These things are all easy to see. Why? Because we started with the factoring and multiplied it out, right? It's like, yeah, if you know the answer, it's easy to do the problem, right? Let's look at one where it's not like that. We're not quite done. Let's see, f of x equals to 10x squared plus 5x plus 15. Can we factor this? I mean, the first kind of factoring that you can think about is just factoring out a number. A number is a polynomial, a kind of silly one. It's a constant polynomial. So one thing we sometimes think about is just factoring out a number. This one I factor out a 5, right? So there you go. Sometimes this is it. We've factored out the integer 5. Look at another example. Suppose I had x squared plus 3x plus 2. Can we factor this? So what I do is I put down myself kind of a blank template. I put x here and here. I think about 2. 2 is what? It's 2 times 1, right? Or it's minus 2 times minus 1. But I don't want the minuses because I've got a plus 3 here. So I do, plus 2, plus 1. I mean, you just got to try something, is the point. You try something, how do you check whether or not you're right? You what? You go back to your FOIL, right? FOIL it out. And see if this multiplied out, goes back to here. If it does, we did it. We unmultiplied. See, this is a very related problem, but slightly different. X squared minus 3x plus 2. See this? And we think about how to get 2, right? I heard a minus 2 minus 1, right? This one, see, I've got a minus 2 here, right? So how do I get a minus 2? I either get a minus 2 by minus 2 times 1 or 2 times minus 1 if I'm using whole numbers. We try whole numbers to start with, right? You're like, are you trying to tell me fractions are going to get involved? It's true. Fractions are coming back. I know. If we want this plus x, that means what? Yeah. If we want this plus x, we better go with the plus 2 because we want it to win. Now FOIL it out. Does it work? We got plus 2x. We've got minus x. So we get 2 minus 1, which is 1. Got it. Do they all work out like this? No. Generally speaking, factoring can be ugly. And in fact, it was proved in the 19th century by a 20-year-old Frenchman, something like that, that for fifth order and higher polynomial equations, like if you set like f of x equal to 0, you know we have the quadratic formula eventually in here. At the end of the course, we'll talk about that. It turns out that there's like no analog of that for fifth order and higher problems. What I'm trying to get at is the problem of factoring an arbitrary polynomial is very difficult. So we will necessarily be looking at examples which aren't that difficult, and they allow for these kind of manipulations we're doing. So anyway, we'll do more next time. Thanks, guys. Oh, Chris, did you hit it?